Assalamualaikum and hi students. So this is a lecture video for BEKG 2443 Engineering Mathematics 2. Okay, for chapter 3 we have vector calculus, and in this video we will cover the first, third and fourth LO. For the introduction, I am very sure that all of you have seen this before. You use these vector functions operations in Engineering Mathematics 1 and Engineering Mathematics 4 Diploma. Okay, so before this, you know what is FTGT, vector for single variable. You have a function T, function in terms of T. Okay, and then you have these 5 operations, products of a scalar and vector. And then you have vector sum, dot products and cross product and product of a scalar function and a vector function. So we will use the same knowledge, the fundamental knowledge for this chapter. The definition is given by definition 3.1, where a vector field of 2 or 3-dimensional space is a function f that assigns to each point x, y for 2 variable for 2 dimension and x, y, z for 3-dimensional vector given by, okay, this one is for 2-dimensional. You have f, x, y. You have 2 variable x and y, and then you have m, x, y, I plus n, x, y, j, or for 3 variable you have f, x, y, z equal to m, x, y, z, I, and then plus with n, x, y, z, j, plus with p, x, y, z, k. So this is the difference between 2-dimensional and 3-dimensional. For 1-dimensional, you have xt, xti plus ytj, for example. Okay, we have one example here. If you are asked to sketch the following vector field given f, x, y equal to minus y, I plus minus x, j. So I and j is the direction of your x and y axis. So I refer to x axis, the direction for x axis, while j is referred to the direction for y axis. Okay. For example, if you want to sketch this vector field, you need to know, you need to state what is your xy point. Okay, start with your xy point and then substitute your xy point into your fxy. Okay, for example, we try with a few points. Let's say 1, 0 for the first point, second point 1, 1, 0, 1, and negative 1, 1. Okay, so for fxy, substitute into this fxy. So minus y, our y here is 0, so we don't have I. Okay, and then minus xj, so we have minus j. Okay, 1, 1, substitute I equal to, substitute x equal to 1, substitute y equal to 1, so you have minus I minus j. So this is plus j, xj. Okay, let's change the equations. So I have plus j, then this is minus I, minus 1 here, so you have minus I minus j. Okay, so for this one, okay, if we have x and y axis, y and x axis, okay, we have 1 here, positive 1, y equal to 1, x equal to 1, x equal to minus 1, and y equal to minus 1 over here. So we have point 1, 0, this is 1, 0, then 1, 1 is here, 1, 0, 1 is this point, and then minus 1, 1 is here. Okay, if you refer to fxy, okay, fxy 4.10, so minus j, sorry, positive j, which we just changed the equation. Okay, so plus j, meaning that you have this straight line with 0 I plus 1j. So j is in y direction. So it moves upwards. Okay. And then for 0.11, this is 0.11. Okay. So 0.11, it moves minus I. So it moves to the left by 1, and then it moves up by 1 for j direction. So you have this. To the left first by 1, and then to the up, you have up 1. Okay. And then from 0, 1. 0, 1 is this point, you have minus I. Minus I, you have to move to the left by 1 point. Okay. And last, you have minus 1, 1. So you have minus to the left, and then you need to go down by 1. So from here, you have this direction. You move to this, minus 1. So minus 1 to the left, and then, so you have this one, Okay. Okay, so you can continue with another points. Let's say I have x, y, f, x, y. For point, to continue with this graph, I'm considering negative 1, 0, negative 1, negative 1, 0, negative 1, 1, negative 1. Okay. So the other point is negative 1, 0, this one. And then negative 1, negative 1, 0, negative 1, and 1, negative 1. So you have this vector field. Okay, if you just consider 8 points. And if you consider many more points, you will have this vector field. Okay, if you see in a bigger picture. Okay. For the second example, okay, match the vector fields F with the plots label 1 to 4. Okay, for A, fxy equal to yi plus, this is yi plus xj. B, you have fxy equal to I plus sin yj. For C, you have x minus 2i plus x plus 1j. And for D, your f is equal to yi plus 1 over xj. Try to do this. Okay, the last answer is, check your answer. Okay, A is the match for number 2. Plot number 2. Okay, B for, okay, C the first one, and D is the third one. Okay. Okay, if f is a scalar function of two variables, then its gradient vector field on two-dimensional space is defined by this nabla fxy equal to, you differentiate your fxy with respect to x. So this is for I, plus fy fxyj. Okay, this is for two-dimensional. And for three-dimensional, the gradient vector field nabla fxyz is given by fxi plus fyj plus fzk. Very simple. As for example, find the gradient vector field of the following functions. Okay, start with function A. So A, I have fxy equal to x squared y minus y cubed. So nabla for fxy, the gradient for fxy is equal to, differentiate your fxy respect to x first. So for this one, you have 2xy. And then this one, you have 0. So you have 2xy for I and 2xy for I. And then for j, you need to differentiate this respect to y. So you have x squared plus with x square minus 3y square g. Okay, gradient for A. For B, continue with B. fxy equal to ln x plus 2y. Okay, so the gradient fxy is equal to differentiate ln x is 1 over x. For I, and then you don't have x here, so you just have y. So for j, you just have 2j. Okay, continue with C. For C, your gradient vector is equal to, first differentiate x, so you have xy exponent xy. Okay, since this is a product, okay, a product, so you need to use the product rule, plus with differentiate x is 1, so exponent xy. This is for I, plus with differentiate respect to y for j. Okay, so for j, I have x square exponent xy j. And this can be simplified and written as exponent xy, x plus xy, this is xy, plus 1, I, plus x square exponent xy j. And last, for D, you have fxyz. So nabla fxyz, the gradient for 3-dimensional space. So x cos yz, differentiate x, you have cos y over z for I, plus with, okay, differentiate your cos, you have minus sine y over z. And then for y, differentiate y, you have y 1 over z. For j, this is for j. And for k, differentiate fxyz respect to z. So you have x differentiate cos negative sine y over z, and then differentiate y over z. 1 over z is ln z, y ln z for k. So the gradient here for D is cos y over z I minus x over z sine y over z j minus x y ln z sine y over z k. Okay. Right, moving to 3.2, subtopic 3.2, we have line integrals. Okay, a line integral, or sometimes we call as a path integral, is the integral of some function along a curve. Normally, we denote the curve as C. Okay, definition 3.2 give the definition for line integral with respect to arc length. Okay, so let C be a smooth curve in 3 space. Okay, x, y, and z, given parametrically by the equations x, y, and z. Okay, we write x, y, and z in t. Okay, function of t, and let f, x, y, z be continuous on some open region containing the curve C. Then the line integral of f, x, y along C is denoted by, okay, so for this one, you need to solve for integration. Okay, integration C f, x, y, z ds can be written as, okay, integration from A to B. Okay, A to B is limit for t. Okay, because you do the integration respect to t, and then f x t, instead of you have f x y z, you write your f in x t y t z t. Okay, so you need to know what is the parametric equation for each x, y, and z, and then you need to multiply with square root of x prime square plus y prime square plus z prime square. So you know that this square root of x prime square plus y prime square plus z prime square is equal to ds over dt. Okay, the arc length of the curve. Okay, so for parametric equation, okay, there are few parametric equation you need to know in order to solve for line integral. Okay, and we will use this a lot in this chapter. So the three parametric equation. Okay, the first one for the line segment. You need to remember this. Okay, for the line segment, let's say you have from x naught, the curve move from x naught, y naught to x1, y1. Okay, so xt, the parametric for x is equal to 1 minus tx naught plus tx1. Okay, substitute x naught and x1 into xt, and then for yt is equal to 1 minus t y naught plus ty naught. Sorry, ty1. The first case for line segment. The second one, if you have a circle. Okay, a circle when you have, let's say, x square plus y square equal to r square. Okay, so xt is given by r cos t and yt is written as r sin t. And the last one for explicit equation. Okay, explicit equation, for example, if you have y equal to fx, you write y in term of x. Okay, so x t will be t. Okay, x will be t, so yt becomes ft. Okay, for example, if you have parabola where y equal to x square. Okay, for this one, xt is equal to t. You define x as t, so your yt becomes t square. Substitute xt with t here, so you have y equal to t square. Okay, remember these three parametric equations. We have few examples here. So start with the first one. Evaluate integral c x y to the power of 4 ds. Okay, ds, where c is the right half of circle x square plus y square equal to 16. Trace out in a counterclockwise direction. Okay, so if you sketch the curve, so you have this x square plus y square equal to 16, the right half of the circle. So you have this with radius 4. This is y, this is x. Okay, and the direction is counterclockwise. So counterclockwise, it moves from below to above. Okay, so for this one, you need to know, first you need to start with the parametric equation xt and yt. So for a circle, xt is given by r is your radius, so radius is 4, x is r cos theta, r cos t, y 4 sin t. And then you need to know the range for t. Okay, so the range for t is from, this one is 3 pi over 2. 3 pi over 2 to pi over 2. Or you can use from minus pi over 2 to pi over 2. No problem. Okay. So first thing first, you need to know what is ds over dt. So ds over dt is square root x prime t square plus y prime t square plus z prime t square. Okay. So ds is equal to ds over dt is equal to square root our x prime t is negative 4 sin t. Differentiate your x. So you have negative 4 sin t plus differentiate your y. You have 4 cos t square. Okay, in this case, we don't have z, so it is okay. We just have what we have. Okay, we just do what we have. So this one, you have 4 square is 16 square. Sorry, 16 sin square t plus 16 cos square t. So move dt here, so you have dt. So ds is equal to square root 16 sin square t plus cos square t dt. And you know from the trigonometry identity, the sin square t plus cos square t is equal to 1. Okay. So your ds is equal to square root 16 dt. And square root 16 is equal to 4 dt. So first you have your ds. Okay, so to find what is integration, the line segment for x, y to the power of 4 ds. So this is equal to, have your integration. Okay, substitute x with your xt. So xt is 4 cos t. Okay, y is 4 sin t to the power of 4. Okay, and then your ds is equal to 4 dt. This is 4 dt. And then for range, substitute your t, range for t. 3 pi over 2, 2 pi over 2, or negative pi over 2, 2 pi over 2. And then we just continue with the integration. Okay, so the line segment for this example is equal to 8192 over 5. Okay, do the integration and then apply the substitution, integration by substitution here. Okay, so you get the last answer equal to 8192 over 5. Okay, second example, evaluate integration C x plus yz ds on the line from P121 to Q210. Okay, so this is an example for line segment. So for line segment, you have xt equal to, okay, x naught. X naught is 1. Okay, so 1 multiplied by t minus 1. Sorry, 1 minus t. 1 minus t plus x1, which is 2, multiplied by t. So this is equal to 1 minus t plus 2t. So I have 1 plus t. Okay, for xt. And then for yt, y naught is equal to 2. Okay, multiplied by 1 minus t plus y1 is equal to 1. Multiplied by t is equal to t. So this one I have 2 minus 2t plus t is minus t. And zt is equal to, for z1 I have z0 is equal to 1. So 1 multiplied by 1 minus t plus 0t. So for this one, I have 1 minus t for z. And then for range of t, so t, okay, for these three parametric equations, what is the value for t? Okay, when I substitute 0 for each equation, I got 1, 2, and 1. I got the p, point p. And then, if I substitute t equal to 1 here, I got, for x, I got 2. For y, I got 1. And for z, I have 0 here. So I have my P and Q point when I substitute 0 and 1. So the range for T is 0 to 1. Then continue, proceed with ds over dt. Okay, for ds over dt, I have the square root. Okay, differentiate x, y, and z. So differentiate x, I have 1 square. Plus differentiate negative 1 square. Plus negative 1 square. So my ds is equal to square root 3 dt. And then solve for c, x plus y z. ds is equal to, my t range is from 0 to 1. And then my x is 1 plus t. Plus with y is 2 minus t, and z is 1 minus t. And then substitute my ds with square root 3 dt. Solving for the integration, I get this integration is equal to 7 multiplied by square root 3 divided by 3. Okay. Next, evaluate integration c y ds, where c is the semicircle. X squared plus y squared equal to 16 from negative 3, 0 to 3, 0. So if you have xy plane, okay, you have x squared, you have a semicircle, x squared plus y squared equal to 16. So the radius is 4. Why is it 16? It's supposed to be 9. Okay, I change the question. This is 9. X squared plus y squared equal to 9. So the radius for this semicircle is 3. Okay. From negative 3. Okay. And then it moved from negative 3, 0. Negative 3, 0 is this point here to 3, 0. This one. So it moving clockwise. Okay, clockwise. So now we start with parametric equation. My parametric equation for x becomes negative 3 cos t. Why? Because it moved from negative 3 to 3. Okay, so the x is minus. Okay, and then y t is 3 sin t. And my t interval is 0, t to pi. Half circle, semicircle. Okay, if the circle moving counterclockwise, so both x and y is positive. Okay, so my ds now, ds is equal to square root negative 3 cos t. Differentiate negative 3 cos t is 3 sin t square plus differentiate 3 sin t, I have 3 cos t square. And then my dt here, so I have 3 square dt, because sin square t plus cos square t is obviously equal to 1. So I have 3 dt. And then I can continue with y ds, integration y ds. I have 0 to pi. My y is 3 sin t and my ds is 3 dt. Okay, you may continue from here. Okay, make sure to check your last answer with mine. My last answer is 18. In line integrals also, we have definition 3.3, line integrals with respect to x, y, and z. X, y, or z. Let C be a smooth curve in 3 spaces. given parametrically by the equations, we have x, y, and z, okay, in term of t. And let fxyz, gxyz, hxyz be continuous on some open region containing the curve C. Then the line integrals is defined by this one. These three. You have, if you want to find the integration of fxyz dx, gxyz dy, or hxyz dz. This is the substitution, okay? So you need to do the integration from a to b, f x t y t z t, and then find what is multiply with what is the differentiation of x for dx, okay? For y, multiply by y prime. For dz, multiply by z prime, okay? So all these f x y z dx, g x y z dy, and hxyz dz, the integration is called the line integral of f, g, or h along C with respect to x, y, and z respectively, okay? So before this, you considering finding the integration of f, x, y, z respect to s. You have ds, but now what if you have x, dx, dy, or dz? Okay, for further understanding, we see this example. Okay, so evaluate integration, see, xy dx plus 3x square plus y square dy over the circular arc C given by x equal to cos t and y equal to sin t for 0t pi over 2. Okay, t is in between 0 to pi over 2. So we know the circle is with radius 1 and the theta, we just considering the first quadrant, pi over 2. T is from 0 to pi over 2. Okay, so to solve for this one, you know your x t is equal to cos t and your y t is equal to sin t. This is given. Okay, so find what is your x prime t. So x prime t is equal to, differentiate cos t is equal to negative sin t dt. Okay, and then y prime t is equal to cos t dt. Okay, you differentiate your x and y respect to t. So that's why you have dt here. Okay, and the t is from 0 to pi over 2. Okay, so cxy dx plus 3x square plus y square dy. This is dx, okay, dx over dt. So instead of x prime, we use dx, and instead of y prime, we use dy. Okay, so this is equal to so the interval t is from 0 to pi over 2, and then x, y. Okay, substitute x and y. X is cos t and y is sin t. dy is equal to cos t dt. This is your dy. Okay, cos t dt plus with integration 0 to pi over 2, you have 3 x square plus y square. X square plus y square is cos square t plus sin square t. And my d, is it dy? Sorry, this is dx. This is dx. Okay, so dx, my dx is negative sin t. Negative sin t dt. So my dy is cos t dt. Simplify this. I have 0 to pi over 2 cos t, negative cos t sin square t dt plus 0 to pi over 2 cos square t plus sin square t is equal to 1. Then I have cos t. So 3 cos t dt. And solve for the integration from here. Okay, the last answer I get here is 8 over 3. Okay, here use the substitution. Okay, substitution, you let u equal to sin t. So du is equal to cos t dt. Okay, so solve for the integration and the last answer is 8 over 3. We also have the line integrals over piecewise smooth curve. Okay, the definition of line integrals with smooth curve C can be extended to curve formed by finitely many smooth curve. Let's say we have C1, C2 until Cn. Join n to n. For example, you have this one. C1, C2, C3. Okay, with different functions. C1, C2, C3. Or C1, C2. Or C1, C2. Okay, so there's a line integral over a piecewise curve C to be the sum integrals over the pieces. So to find what is the line integral for C, you need to solve segment by segment. Okay, solve for C1 plus with C2 plus with C3. Okay, for example, if you have C consists of a quarter circle, x square plus y square equal to 4. Okay, a quarter circle means you have x, y, y and x. Quarter circle, radius 2, x square plus y square equal to 4. Okay, radius 2. From 2, 0, 2, 0 is this point. 2, 0, 2 to this point. This is 0, 2. Okay, it moving counterclockwise. And so this is our C1. And the line segment from 0 to, this is 0 to 0, 0. 0, 0 is here, point origin. So it moving downward. Okay, so this is our C2. So you have different curve. Okay, so to evaluate the line integral C, x dx plus 2y dy, we need to solve segment by segment. Let's say first we consider C1. For C1, x1t is given by a circle. Okay, so for circle we have 2 cos t and y1t is equal to 2 sin t. And of course, our t is from 0 to pi over 2 since it is a quarter circle. Okay, and then find what is dx dt, what is dx and dy. So dx is equal to negative 2 sin t dt and dy is 2 cos t dt. Okay, so for C1, x dx plus 2y dy is equal to, okay, so our t is from 0 to pi over 2. Okay, x dx, x is 2 cos t, dx is equal to negative 2 sin t dt plus 0 to pi over 2. We have 2. So 2 and y is 2 sin t. dy is equal to 2 cos t dt. Okay, try to solve for the integration for C1 first. I just solve for C1, integration for C1. Okay, and the last answer is 2. Okay, here from here, 8, I have 8 sin t cos t and minus 4 sin t cos t. So I just have 4 here, 4 cos t sin t, and then use the substitution u equal to sin t to solve for this integration. Okay, now we can continue with C2. Okay, for C2, it is a line segment from 0 to 0, 0. So for line segment 0 to 0, 0, my x 2t becomes Okay, for x2t, 0 and 0. So I don't have my x2t. So x2t equal to 0. So I don't have dx. I don't have dx. Okay, no dx. Since my x2 is 0. Next, for y2t. For line segment y2t, my y0 is equal to 2 and my y1 is equal to 1. So 2 multiplied by 1 minus t for the line segment. So my dy, okay, differentiate this negative 2t, I have negative 2 dt. Okay. Okay, so for C2, x dx plus 2y dy. So this is equal to the line segment. Range for t is from 0 to 2. Sorry, so 1. Okay. Okay. So 0 to 1. Okay. I don't have x. X is 0. So 0. So just focus with 2y. So 2y is equal to 2 1 minus t, and my dy is equal to minus 2 dt. Okay, so I have 2, negative 8 from 0 to 1, and then 1 minus t dt. Negative 8 t minus 1 over 2 t square from 0 to 1. So this is negative 8. 1 minus 1 over 2 is 1 over 2. So negative 8 multiplied by negative 1 over 2 is equal to, no, this is positive 1 over 2, negative 4. So my C1 is equal to 2. My C2 is equal to negative 4. So we can conclude that C, okay, integration C, line integral C, x dx plus 2y dy is equal to 2 plus minus 4, which is equal to negative 2. Okay, you add up the line segment for C1 with C2 for line segment C. Okay, so the last answer is negative 2. Okay, the last one for line integrals. Okay, we have line integrals in vector form. Definition 3.4. Line integrals in vector forms. Let C be a curve, a smooth curve in 3 spaces given parametrically by the equation. Okay, as usual, we have x, t, y, t, z, t. And let f, x, y, z, g, x, y, z, h, x, y, z be continuous on some open region containing curve C. Then the line integrals along C is written in vector notation. So for vector notation, you have I, J, K. Okay, I, J, K. F for I, G for J, H for K. The curve C can be expressed in terms of position vector. Okay, RT, you know what is RT. RT is equal to XT plus YTJ plus ZTK. Okay, displacement. Okay, there's the work. Okay, now we talk about the work. Okay, line integral in vector form give you the work W by a continuous force F. Okay, the range for T is from A to B. So the work is equal to F x y z dr equal to integration from A to B f x t y t z t multiplied by r prime t dt, or we can write this as integration from A to B f r t. Okay, x y z t is equal to r t. Okay, dot product with r prime t dt. So here you need to know how to solve for dot product. One example here we have, find the work done by a force F equal Fxyz equal to y minus 2zi plus xyj plus 2xzk, where C is the curve xt, x equal to t, y equal to 2t, plus z equal to t square minus 1 for 0, for t from 0 to 1. Okay, for this, to find the work, okay, to find the work done, you need to start with find what is your RT. Define what is RT. So you know RT is equal to XT plus XTI. XTI plus YTJ plus ZTK. Okay, so put all X, Y, T together in R. So this is your RT. Second steps is find what is R prime T. Okay, R prime T is equal to, okay, differentiate T, you have 1, so I, plus 2T, you have 2J, plus T square minus 1, I have 2T, K. Okay, this is my R prime T. Just differentiate one by one for I, J and K. And then substitute your Fx, Y, Z, which is equal to Y minus 2ZI plus X, Y, J plus 2XZK. Okay, substitute this into FRT. To find what is FRT, okay, substitute your Y with T. Okay, so Y is 2T minus Z is T square minus 1. So 2 multiplied by T square, so minus T square plus 2. I plus XY, multiply X and Y, so I have 2T square. J plus 2XZ. 2XZ. So I have 2T cubed minus 2T. X and Z, is it? Yes. K. Okay, so this is my FRT. So now I have FRT and R prime. So to find the work done, okay, so 0 to 1, the interval for T, okay, 0 to 1, and substitute my FRT. FRT is 2T minus 2T square plus 2I plus 2T square J plus 2T cubed minus 2T K. Okay, dot product with R prime. R prime is I plus 2J plus 2TK dt. Okay, so 0 to 1. Okay, dot product, you multiply I with I. So 2T multiplied by 1 is 2T. 2T multiplied by 1 is 2T. Minus 2T square multiplied by 1 is minus 2T square. Plus 2 multiplied by 1 is 2. Then you don't have any I. Okay, because I square is equal to 1. Okay, it becomes a scalar. Okay, you don't have I anymore. Plus with, multiply J with J. Dot product J with J. So you have 4T square. No more J. Plus 2T cube multiplied by 2T is 4T to the power of 4 minus 4T square dt. No more K. Okay. Okay, you can proceed from here. And as I proceed with the integration, I get my work done equal to 47 over 50. Okay, this is how you solve the line integrals in vector form. We come to the last example for this video. Okay, find the work done if a particle move from negative 2, 4 to 1, 1 along the parabola y equal to x square while subject to the force. Okay, you have the force F, xy equal to x cubed y I plus x minus yj. Okay, so parabola y equal to x square. So you have y equal to x square. Okay, this is y equal to x square. This is x and y. So point negative 2, 4 is somewhere around here. So let's say this is 4 and this is your negative 2. 1, 1. 1, 1 is here. We have 1, let's say, and 1. Okay, so from it moved from this point to this point. Okay, so first thing first, we need to find the parametric equation. Okay, parametric equation xt and yt. For explicit equation, okay, we just can consider x equal to t. Okay, so xt is equal to t. So my yt is equal to t square. When I substitute x equal to t, so my yt is equal to t square. And then for range of t, okay, the range for t is from -2 to 1. Why? Because if I substitute -2 to t, I get -2 and 4. And then substitute 1 here, I have 1 to 1. So I get back my point, p to q. Okay, that's why you need to carefully consider your t. Okay, the range for t. Okay, from x and y, I can write my rt. rt is equal to ti plus t square j. And I can find r prime t, then I have I plus 2tj. Okay. Okay, next I can find what is my FRT. FRT refer to here. So x cube. X cube is t cube multiplied by y. Y is t square. So this is for I. Okay. Plus x minus y. X is t and y is t square for j. So here I have t5i plus t minus t square j. Okay, I have my FRT and R prime t, so I can find what is the work. Okay, works is equal to -2 to 1, my t. And then FRT is t to the power of 5 I plus t minus t square j dot product with R prime I plus 2tj dt. So -2 to 1, t to the power of 5i, I have t to the power of 5 plus 2t square minus 2t cube dt. So proceed with the integration. Okay, and the last answer you should get is 3. The work is equal to 3. Okay, make sure to check this last answer. Okay, so that's all for this video, the first video of lecture 3, chapter 3. Okay, so for the next video, I will explain about subtopic 3.3, which is Green's theorem, and 3.4 we have curl and divergence. Okay, so that's it for this video. Thank you.